tutorial, we will be discussing standard energies and Gibbs free energy. Gibbs free energy is the maximum amount of work energy that can be released to the surroundings by the system that is at the constant temperature and pressure. Often called the chemical potential energy because it is analogous to the storing of energy in a mechanical system. The energy in a chemical reaction uses to do work. This is the energy available after bonds are broken and formed to do chemical or biochemical work. A thermodynamic quantity that combines enthalpy H and entropy S into a single quantity. G for Gibbs is equal to enthalpy H minus T for temperature times S for entropy. The change in the free energy is a theoretical limit as to the amount of work that can be done. If the reaction achieves its theoretical limit, it is a reversible reaction. In a real reaction, a non-ideal condition, some of the free energy is lost as heat. Real reactions are irreversible. Negative T delta S of the universe is defined as the Gibbs free energy. When the delta S is positive, this negative sign makes delta G negative. Therefore, when delta G is negative, the process is spontaneous. So let's take a look at this. This is the free energy increasing. If delta G is negative, going in this direction, going down, the forward reaction is spontaneous. If delta G is at 0, it is at equilibrium. When delta G is positive, the reaction is spontaneous in the reverse direction. So let's talk about spontaneity a little bit more. Gibbs free energy value is the combination of enthalpy and entropy at a given temperature for a system. Delta G of the system is equal to delta H minus T delta S. Delta S of the universe determines whether the process is spontaneous. Delta G also determines spontaneity. Delta S of the universe is positive and spontaneous, but delta G must be negative. Its value predicts the direction of the chemical reaction. If it's positive, it's non-spontaneous. If it's negative, it is spontaneous. And if it's 0, it's at equilibrium. So let's look at the possibilities of what can happen at different signs. So if delta H, remember delta G is equal to delta H minus T delta S. If delta H is negative and delta S is positive, it's going to be minus and then minus. This means it's being an exothermic reaction and it's more random. It's automatically going to be negative. If delta H is negative and very large, it overpowers a negative small delta S, meaning that it'll still be negative. If the delta H is positive and very small, then the delta S needs to be positive and very large for it to still be negative, which means that it'll occur, or if it's at a very high temperature, because then the T, if this is delta S is positive and the T is very big, it'll overpower it. Delta G is positive when delta H is positive and delta S is negative. When this occurs, it's never spontaneous regardless of the temperature. And delta G is 0 when it's at equilibrium. There are two different ways of calculating delta G. First of all, you can use the delta H of formation and delta S of formation that we've done in the past to calculate this equation. This will be done in a future tutorial. In this tutorial, we're going to be discussing it this way. The use of the tabulated values of free energies of formation. So once again, you're looking up a chart to determine the delta G's and doing the products minus the reactants. The delta G of formation values for elements will be 0. Analogous to the standard enthalpies of formation are standard free energies of formation. So in other words, the delta G of a product times the coefficients minus the delta G of the reactants times its coefficients, and then subtract the two. So let's do a practice of these. Graphite, you'll notice, is 0 for delta G because that is pure carbon. Also, oxygen is 0 because it's pure oxygen, it's a pure element. So we're going to take the products minus the reactants. So that means CO2, we don't have any coefficients there, minus C graphite and O2 gas. Alright, so that means CO2 is negative 394.4 minus graphite is 0 and oxygen is 0. So that means our answer is negative 394.4 kilojoules per mole, which means it is spontaneous because it's negative. Alright, let's try another one. The products minus the reactants. So the right side minus the left side. So CO2 is right here, negative 394.4. I don't have a coefficient. Plus 2 from right here times water, negative 228.6, plus 4 from this coefficient times ozone, 163.2. Add all that up, and then we're going to subtract out the reactants. So the reactants are, there's no coefficient here, so it's negative 50.5, and oxygen is 0 because it's a pure element. So negative 394.4 times 2, or plus 2 times 228.6 plus 4 times 163.2 minus 50.5 minus a negative. So it ends up adding. So that comes out to be 148.3. Let me repeat that. The products minus the reactants. 394.4 for the carbon dioxide plus 2 times negative 228.6 plus 4 times 163.2 minus the reactants, so minus negative 50.5. So you're adding 50.5 to 148.3 kilojoules per mole. Alright, the last way we're going to do this is if we had chemical reactions, and the chemical reactions gave us the delta G's rather than looking them up in a chart. If a reaction can be expressed as a series of reactions, the sum of the delta G values of the individual reactions is the delta G of the total reaction. So it's the same idea, but instead of looking up all the delta G's individually, it might be a multi-step reaction. And then you have to sum up all the multi-step reactions. Delta G is a state function. Therefore, if a reaction is reversed, the sign of delta G values reverses. And delta G value is multiplied by the reaction stoichiometric factors. The value of delta G of a reaction is extensive and phase specific. Alright, so what I meant, this number over here, negative 2,074 kilojoules. That's the amount of delta G's. If we were to look up in a chart and looked up H2O, CO2, O2, and C3H8, if we looked those up, that would be the delta G with the products minus the reactants. Now, this particular reaction up here evidently takes 3 steps to complete. 3 different reactions have to occur in order for the final reaction to occur. So we're going to rearrange these three to make it look like this one on the top. The one on top is our goal. So, for instance, C3H8, that's on the left-hand side here. And our goal is on the right. So we're going to flip around this equation. As a response to flipping it around, I have to change that negative value here to a positive. Let's go to the next step. I have carbon on the left here. I have carbon on the left here. So we're good. But you'll see that it's getting multiplied by 3. So that means I have to multiply the entire equation by 3. So now it's 3 carbons plus 3 O2s yields 3 CO2s. Because I multiplied that by 3, I have to multiply the delta G by 3, which then comes out to be negative 1183.2. Finally, let's look at this last equation. We have H2 plus O2 yields H2o. Once again, I have H2 on the left, and I have H2 on the left up here, so we're okay. But you'll notice that the bottom one has 2 hydrogens, while the top one has 4. I want to make sure that's the same amount, so I'm going to multiply the bottom one by 2. So 4H2 plus 2O2 yields 4H2O. Because I multiplied that by 2, I want to multiply the delta G by 2, which comes out to be negative 914.2. We want to cross out ones that we can, like algebra, or if we're adding up mathematical equations, just like that, and try to minimize it and try to look exactly like that one on top. So for instance, we don't have any oxygen on the top equation. So let's see if I can cancel out the oxygens. I have 5 here, I have 3 here, and 2 here. So 3 plus 2 is 5, so I can cancel those out. I have water down here, but I have no water up here. I can cross it out from left to right. Same with the carbon dioxide, 3 and 3. So you'll notice what I have left over is 3 carbons, 4 H2s, and C3H8. I know I did it right now because I have everything on the left I'm supposed to have and everything on the right I'm supposed to have. The last step you want to do is add up the delta G's. So that's positive 2074 plus negative 1183.2 plus negative 914.2. That comes out to be negative 23.4. Because it's negative, that means this reaction is indeed spontaneous. And that's how you calculate delta G with a product with a free energy formations.